Thank you for joining us today. Um, we have two speakers who will be talking about AI and machine learning, and they will be helping you train your first neural network as well. Our two speakers are Jacob George and Mike Bien, and I'll give a quick intro on both. Jacob here is a consultant at IBM in data science, and he did his bachelor in mechanical engineering from the University of Alberta and his master's from the University of Calgary in biomedical engineering before joining IBM. And Mike did his bachelor's at the University of Waterloo with a bachelor's in computer science with a minor in physics, but he specialized in machine learning and AI. So now he is also working at IBM in machine learning and AI. So without further ado, I'll just let Jacob and Mike take over now.
Awesome. Thanks for the intro. Hey, everybody. Thank you all for taking time out of your Thursday evenings to come attend this. We wrote up a quick machine learning 101 session for all of you, and kind of what we wanted to do out of this session is really attend to those who are like not that familiar with machine learning. We wanted to build a session to really lay down the groundwork, get people building their first neural networks, and then also just to get some perspective and understand what's going on in the industry these days. What are some current challenges that are faced? So before we get right into it, I'll just start with a little bit about ourselves. So,
Sorry,
so yeah,
there's some background noise. Can we ask everyone just to turn off their mics? We'll have breakout sessions later on for Q&As and everything. So we'll talk then, but just for now.
Yeah, that's a great point, Mike. Yeah, so we'll just ask everyone to hop on to mute, and yeah, we're gonna do breakout sessions in a bit. Once we get into that, feel free to throw yourself off of mute, and then we also have a Q&A session at the end where you can write in questions either on the chat or you can just come chat with us. So yeah, so a little bit about myself. I'm a data scientist and consultant at IBM. So what that kind of means is what I do is I work for IBM, but I'm sent to different companies that want to use artificial intelligence and machine learning, but don't really know how to. And so then people like me and my team will go in and evaluate how we can use machine learning to improve the current company practices and workflow. And we'll see a few use cases of what that could even look like a little bit later on here. I did my master's at the U of C, and then I did my undergrad at the U of A before that. I'll pass it over to you, Mike.
The target vector, because this.
Okay. Sorry, I was on mute. So hey guys, I'm Mike. Like Henny said, I come from a computer science background from the University of Waterloo. I'm actually on Jacob's team, or we work closely together. And I'm a machine learning engineer. So similar to what Jacob said, I'm also a consultant. Yeah, we go to different companies. We provide AI solutions for our clients, and kind of the roles that we take. Jacob is the data scientist, so he's the one that's building all the AI models, the ML models. I'm the machine learning engineer, so I engineer the systems to run them. I help him with the data pipelining coming in, how to actually use the model, because a good model is a good model, but a good model doesn't run by itself. So that's basically where the machine learning engineer background comes in.
Yeah, absolutely. So to talk about today, so we're going to be talking about four main things. So firstly, we're going to build that foundation. We're going to talk about what are we talking about when we talk about artificial intelligence? What are we talking about when we talk about machine learning? and we're gonna lay some foundations so that everyone's kind of on the same page here, and then we're gonna hop right into a demo. So Mike took the time to make us a pretty awesome demo that we're all going to be playing with, and we're going to be building our first neural network. After that, we're going to look at some use cases and see both where big companies have implemented machine learning solutions that are really integrated into our day-to-day lives. But we're also going to look at specific use cases of even some people out of Calgary, what they've been working on. Finally, we're gonna look at some future opportunities as well. So I'm gonna just touch on some of the challenges that machine learning faces today, and what I don't know the top researchers and scientists are doing to address it. So yeah, so to start off with, we'll start with an introduction into artificial intelligence and machine learning. So a good starting point would be to dispel a little bit of confusion. So the words artificial intelligence, machine learning, and deep learning, they're used fairly interchangeably, and they refer to similar concepts, but they're not the same. They're each distinct concepts. So if you recognize the image on the right, that's just a bunch of Russian nesting dolls. And what's cool with Russian nesting dolls is you can pull off the top doll, and there's a second doll within it, and there's a third doll within that, and it kind of just goes on inwards. And that's a good analogy of how to think of these concepts, with artificial intelligence being the big broad concept, machine learning living within there, and then deep learning living as a subset of machine learning. So there's a bunch of smart people who try and make this distinction. I have some quotes here on the left. If you don't like to read, which sometimes I don't like to read, I underlined just the important stuff, and yeah. So essentially, what I'm trying to communicate there is what artificial intelligence, what it would encompass is any kind of computer program that does a task that we would think that would require human intelligence. So if you drew a curtain up and there was a computer or a human on the other side, you wouldn't necessarily be able to tell, because it's responding to your inputs well enough to be indecipherable. Machine learning is a subset of artificial intelligence, and it refers to like a specific set of programs that have this really unique functionality. What they can do is they can automatically improve through experience. So typically with programs, you would need a programmer to go back in and tinker and tweak the program if we want to see different results. With machine learning programs, they're fairly unique in the sense that to a certain extent, they can improve themselves. And deep learning is just a subfield within there that uses a specific algorithm called a neural network, which we'll be talking about in a few slides here.
And you'll be building today yourself.
And that everyone's going to be building today as well. So to start off, to kind of put some context into what those concepts mean, because that's a little bit abstract, we're going to talk about something that happened just over 20 years ago now. So this is an image of Garry Kasparov on the left there. He was a world-renowned chess champion. He was a grandmaster. And then on the right there, you see a computer with a dude looking at it. So that was IBM Deep Blue. So the story takes place in 1996, and kind of the background into what happened here is, before this, IBM was working on this world of artificial intelligence. And what they wanted to do is they wanted to create a bot that could play chess. So they created this program, and they used a lot of different algorithms to make this work. And eventually it got to a point where they were so confident in its ability, they decided to take on the world grandmaster, Garry Kasparov. So what they did is they did a round of 6 matches, and Kasparov won 4-2. So that was cool. So Kasparov won. That's awesome. But it's interesting that the computer won twice. And IBM found it interesting too, because they took that back and they worked on it for a year, and they came back in 97 and they challenged Kasparov to a rematch. And they actually ended up beating Kasparov in the next match of 6, 3.5, 2.5. So that was kind of one of the first very public displays of machines beating humans at tasks we thought that humans would always be the best at. And since then, we've heard of a number of different improvements on this. And even now, if you have just like a basic chess app, it can typically beat a lot of really good humans as well. So take this back to like artificial intelligence, machine learning, deep learning. What I mentioned about artificial intelligence is that it needs to be smart enough that it would appear that it was a human on the other side. So if Kasparov couldn't see IBM Deep Blue or the person controlling it, would he think there was a human on the other side? Probably, because nobody's ever beaten a chess grandmaster at chess before at this point in time. So that would kind of fall within the realm of artificial intelligence. But was it machine learning? And that piece about machine learning was that it can automatically self-improve, right? So to look at that, we need to kind of dive into how Deep Blue worked. And so what Deep Blue used was this thing called expert level systems. And what it is it's essentially just a series of decision trees that just map out every possible outcome. So if you look at the image on the right there, there's so I made a little bit of an analogy towards tic-tac-toe, and the way a decision tree would work is that it would analyze the current state. So on the top blue box, we see that nobody's played yet. So then there are potential opponent moves, and you see 3 of them there. And then based on those moves, the computer could make a certain amount of moves, and each of those moves has a certain probability of success or failure, depending on how the opponent would move after that. So essentially what Deep Blue would do, or what this decision tree on the screen would do, is it would, based on the way someone would react, it would evaluate these are all the possible outcomes and would pick the one that was kind of most favorable towards it winning. So it's pretty deterministic. It doesn't actually improve itself. So it's artificial intelligence, not machine learning. And some of the other drawbacks of these types of systems that were really popular in the 80s and 90s is that they take a lot of work to build, because you have to program in every possible outcome. And then if there's something you didn't program in, something that was unseen, it wouldn't necessarily react well because it wouldn't actually know what to do. So as we talked about earlier, the way that machine learning is different is that it uses that concept of learning. So let's talk about what that actually looks like. Or actually, before we talk about what it looks like, we're going to talk about how machine learning is split up. So it's split up into 3 different categories. So the first type of machine learning is called supervised learning, and kind of to put it into context, we can imagine if this algorithm was a 3-year-old. For supervised learning, what you would do is if you gave it a task to do, you would show the 3-year-old this is the right way to do this task, and then you would let it do it. And if they did it wrong, you'd say, no, this is the right way to do the task, and go back and forth until it actually learns the task. The other major field of machine learning is called unsupervised learning, and you can imagine if you see a bunch of if you see a task and you ask the 3-year-old what groups do you see, it would naturally group things up based on some characteristics that are obvious, maybe color, maybe shape, maybe size. But we're not telling it what groups to put it in. The 3-year-old or the computer would actually just determine what is important by itself and group things up like that. Finally, there's reinforcement learning. So reinforcement learning is all about is all about setting the rules of the environment and letting the computer or the 3-year-old to try something out, and then you'll just tell it, okay, this is right or this is wrong, try it again. And you will get rewards when you do things right, and you'll get penalized when you do things wrong. For the purpose of this talk, we're just going to focus in on supervised learning. And so you don't necessarily need to know too much about the other forms of machine learning, but I just put this here so that you gain context of what all machine learning is out there. So this is kind of what a machine learning system would look like. So this is kind of my abstract picture of what a machine learning system would look like. So there would be some sort of input data that feeds into machine learning function. Now this function can be a whole bunch of different things, but the most important thing is that it has to spit out some kind of prediction. And then after it makes that prediction, it's compared against the ground truth. And based on how close or far it is to that ground truth, we're going to update the way the function works so that the next time it makes a prediction, it's going to actually get closer to that truth. So the interesting thing about this is that we're not actually telling the machine what to look at. The machine is going to look at whatever it wants to look at by itself. And and we found that over time, and with a lot of tuning, that this can actually produce improved results based on the ways that we necessarily see things. To maybe put that into a more concrete example, we can talk about house prices. So if you were looking to go buy a house, there's a whole bunch of things that matter. There's the location, there's the house size, the number of bedrooms, bathrooms, and a whole bunch of other things as well. And based on all of these, there is a house price that is determined. So one way that a machine learning algorithm would try and guess this house price is it would take in all these input variables. So it's taking in the 2194 square feet of the house size, the 4 bedrooms, the 3 bathrooms, the location, which could be like a 6 out of 10. So in kind of like an okay, kind of nice area. And it's just going to assign some arbitrary weights to it. So in this example, that's everything that's boxed in the purple, the 10, 1,000, and 50,000. And we're just going to add it all up together, and it's going to give us a number, and that number is 328,000. So now, in actuality, if it was different from that, what the computer is going to do is, based on the difference between the prediction and the truth, it's going to update the weights, and it's going to throw those new weights back in the model. And we're going to use a new piece of training data, run it through the model again, and try and see, did we get closer to the truth? So this way that I have it outlined here, this number times 10 plus 4 times 1,000 plus 3 times 1,000, that's one way to represent a machine learning model. But machine learning models are actually quite generic. So the main point is that it follows this kind of a system. It doesn't necessarily need to be this something times something kind of framework. Another example is if we go back into our decision trees, what we kind of saw before, it could be something like, is the house larger than 2,000 square feet? Then that'll add like 100,000 to the house price. Is it larger than 3 bedrooms? That adds 20,000 to the house price. And so on and so forth. Now, to move on to deep learning, what we're going to be playing with today, it functions very similarly to machine learning. As you can see on the picture on the right there, it has that same generic framework. It has the same feedback loop where it improves based on what the truth is. But the major difference is it uses the specific thing called a neural network as the modeling function. And the deep part of deep learning comes from kind of the number of layers in this network. So the number of horizontal lines in here. What a deep neural network does is that it just creates abstractions of the data. So if you imagine this being our 4 input variables, size, square footage, bedrooms and bathrooms. All of the nodes on the next layer, they're taking all of those and putting, again, some random function to it to generate a new number. And it's going to do that so on and so forth until it comes up with some sort of a prediction. And all those weights are adjusted as it learns more and more. Some of the major differences between deep learning and regular machine learning is that deep learning tends to take a lot of compute, and we'll kind of see that in a little bit. It's quite performance intensive, and it's a little bit more of a black box than traditional machine learning models. So I hope you were paying attention, because we're going to dive right into it. We're going to start building our first neural networks, and before we do that, we're going to be playing with some image data. So we're going to do a little bit of a primer on computer vision first. So those of you who are not familiar with image processing, I just wanted to outline the slide here to get us all kind of on the same footing. So the image on the left there is just an image of an 8. It's pretty pixely and blurry. And to us, we just see blacks and whites on there. What a computer would see is the different intensities of each of the pixels. So it would classify the blacks as 0 or some value very close to 0, and it would classify the whites as 255. That's the brightest white it can get. So the picture in the middle there is just those layers layered on top of each other. So we can see that those transitions between the 0/1 or 0 to 10 to the like 200 something, those would kind of be like the edges of that 8 that's there on the screen. And we can use this change in pixel intensities to detect edges or curves or something like that as well. So just to kind of put that into context for you, like take a moment and think about, so this is an 8. Some of the things that we think of that distinguish 8s are, you know, the two circles, the circle on the top and the circle at the bottom at the center of the 8, the kind of like roundness of it. Those are kind of the things that we would think about when we're distinguishing it from like a 1 or a 2, for example. So that's some logic that can be written in to classify that from something else. But we can take that and we can take it into a more broad application as well. So this is a whole bunch of images of dogs, and these are dogs taken from a really famous data set called the ImageNet data set. So what they do in the ImageNet data set is that there's a challenge that's held every year where researchers around the world try and classify all these images into these categories that you kind of see up there. So there's a lot more than dogs, but I just threw the dog ones up there right now. And it can be images from different angles. It can be zoomed in, zoomed out, warped a little bit. It's just real life style images. And what the researchers would do is they would try and create computer algorithms to read these pixel intensities in these images, so that they could classify these images. So if we think of like back to 2011, right before neural networks kind of hit the scene, people had some really intense algorithms that they were using, and they had this accuracy of about 75%, which is pretty incredible. 75% of the time they could get this right. In 2012, the first year that they actually used neural networks, that accuracy jumped up from 75% to 84% in 1 year. Huge game-changing difference for this industry. From 2012 to now, it's gone up to 95%, and a lot of people even consider this data set, which was considered impossible 10 years ago, to be almost a standard now, like a kind of a baseline and a jumping point towards more difficult networks. So with that, we're gonna see what these neural nets are all about. So we're gonna go into a little bit of a case study here. where we're going to be doing some fashion classification. So we made up kind of a sample scenario here. If you imagine you're a data scientist at Goodwill, now Goodwill, they get all these clothes that are donated to them all the time, and what they need to do is they need to kind of sort them out into different categories, right? They need to sort out their t-shirts, their trousers, their sweaters, dresses, etc. And once they sort it, then they can clean it, put it on the shelves, sell it to new customers. But Goodwill's been getting a lot of donations recently, and they don't have the manpower to sort all these clothes by themselves. So they came up to you as the data scientist and they said, hey, why don't you use some of this fancy machine learning stuff to help classify these clothes? So we're going to build a little conveyor belt, and we're going to take pictures of every item of clothing, kind of like what you see there on the right. And we want you to classify it into one of these categories so that we can get the robots to pluck it and put it into a bin so that we can wash all of these things together. With that, we're gonna, Mike is gonna post a link on our chat, and just hop on that link. You'll probably need your Google account to sign in, and we'll get Mike to walk through the notebook there to kind of explain what's going on. So Mike, I'll hand it off to you.
Okay, awesome. Thanks, Jacob. So if everyone goes into the chat, there should be a link there. That should open up a notebook. It's a Google Collaboratory notebook that we will be using. I will be sharing my screen. I'll share my screen just right now, and just walk us through some of the main parts of the notebook. But basically, you'll be doing it all on your own. We're going to break everyone up into breakout sessions, into groups of 5. And you can talk among yourselves, help each other out, and just go through this notebook. It's all hands-on. You'll be building it on your own. Instructions are in the notebook. And there's a part where, for those of you who might be a bit more advanced, or more experienced with machine learning, you'll be able to create your own customized neural networks. So let me share my screen, and then I'll walk us through some important parts. So let me see. Jacob, if you can take over for just a moment. I might have to drop out and come back into Zoom to share my screen.
There we go. Yeah, we can see it now. Oh, it's Jacob's screen, okay.
Hey, Jacob. Are you muted?
Oh, thank you. Appreciate that. So I hope you guys can see my screen. Can you see a screen that says AI Workshop?
Yep.
Okay,
Yep.
Perfect. So the first thing that everyone's going to do is we're going to hop into runtime, just at the top here. We're going to change our runtime type and we're going to change our hardware accelerator to a GPU. So that's going to allow us to access more processing power. That'll let us run this notebook a little bit faster. So a little bit of an intro into Google Colab if you've never used it before. What you can do is you can click into all of these. So there's some areas that are just text, and then there's some areas that are code. So to run the code, I think what you can do is you can hit this play button, and you're gonna get this warning sign. That's okay. We're not gonna install anything funky onto your computers, but you can hit that play button, or there should be a run all that you can hit just at the top here. But before you hit something like run all, something that I'd like to encourage everyone to do is just throw in your name onto enter your name. Mike.
Thanks, Jacob.
Oh, you're good to go?
Yeah. Yeah.
Cool.
Back. So I'll try sharing my screen again.
Yeah, I'll pass it back to you.
Okay. So thanks, Jacob.
No worries.
Yeah, just had to get my Zoom sorted out. We don't normally use Zoom. But you guys can see my screen now, right?
Yeah.
Yeah, the screen, it's a little bit, okay, there we go. Yeah, just got to zoom in, perfect.
Okay, awesome.
Yeah, it's a
So-
bit small.
I'm sorry?
Yeah, now it's better. Awesome. Thank you.
Okay. Yeah, I think I heard Jacob went through the setups. So instructions are on here, but I'll just mention it one more time. The runtime just needs to be set to GPU. This way, like Jacob mentioned before, AI is very computationally expensive. So with a GPU, it will run much faster. And then once you set that, you can start running it. Like Jacob said, type your name in here. And the reason for this is because we actually have a leadership board. So we will be seeing how well your networks do and be racing against each other, I guess, or not racing, but competing against each other. So just type your name into there, and then we have code to run by just clicking the play button wherever you see it. So every single block, if it's just text, there's nothing to click, but if it's code, you just need to hit it. This warning will pop up. That's all right. We're not authoring this notebook by Google, so because we wrote this ourselves, so just run anyways. Don't worry, it's not running on your machine. This is running all on the cloud. This is using Google's CPU, GPUs, everything. They have, basically there's a machine in Google's server that's running this code for you right now. So like I just showed you, the two cells of code have been run. And then you just need to go through and start hitting these. Or also, like Jacob said, you can hit run all. And one thing that I wanted to show you guys, this is what the data looks like. And then one thing down here, we have something called a tensor board, which will show you how your models are running. So as an example, I will start this. Something like this will show up, and just there's some instructions on how to make it show data in real time. So just go into here and reload the data. So now when you start training your networks, which is right here, we have 4 different networks, and I'll walk us through the differences between them. After we've got everyone has a chance to work through it a little bit. we can actually see these training in real time, these networks being trained. So as you can see here, something's going on. This is the network being trained, or you can also think of it as the network learning. And if you look up here, you actually see the results. So at the very beginning, the accuracy, so you can see the accuracy for train and for testing, for testing and for training, testing and training over here. You can actually see the accuracy start to go up. There's some tools down here that will help you view this data like this. It just helps you focus the data into view. And then once you start running some of these other networks, you'll be able to see multiple lines for multiple networks being trained up here. So once you've gone through that, you would have trained 4 different networks, and you'll be able to see which one works better. And I'll talk a little bit about the differences between these networks afterwards. So let's go into the breakout sessions and have a leadership board over here. A lot of you are too busy for names, I see. Just running through it. But looks like in top position is Quinn right now with 75% accuracy. So that's pretty good with network B. But Henny, let's break out into the rooms. And in your rooms, just talk among yourselves, help each other out. Camera on or camera off, doesn't really matter, but Jacob and I will be jumping into these different rooms just to help out if anyone has any questions. So yeah, let's get started. Hi everyone, welcome back. So I got quite a few questions about it is going through the code, just like hitting run on everything, what we're supposed to do. And that actually is. The exercise is to show you guys that training AI, running this isn't hard, right? Like you guys see that running it took what, seconds, minutes to run, and your accuracy should be around like 70–80%. And that's the whole point. Now, to give you some context, this data set has 60,000 images of clothes. You guys got 70 or 80% accurate after a few minutes of training models. That means that this model, if you put it into production, can go through all of these in no time, and it's going to be 80% accurate. If you have a person do it, think about how long it would take to go through 60,000 images of clothes and put it into the different categories. So that's the power of AI. Now, I also got some questions about what I'm looking at here, and like what is accuracy, what is loss. So to give a bit of a summary on what it is, because we can get very into detail about what the numbers actually mean and the math behind it. And if you're really interested, stay for the Q&A afterwards. Ask me, and I'd be glad to get into it. But just summarizing it, what loss is loss is a measure of how good your networks are doing, how good it's performing, while accuracy is a measure of how good the results are. And you might be thinking, oh, that's the same thing, but it's not quite the same thing, because loss tells us the direction that your network should be going in. So as an example, if your network is 80% accurate, that means that for 80% of the cases, it got it right. And then for 20% of the cases, it got it wrong. That's what accuracy means. But it doesn't tell you how much it got it right. And these networks, like Jacob said before, they're probabilistic. So they're not telling you this is the case. It's telling you it's most likely. So for example, your networks over here is looking at this dress over here, this picture over here, and saying it's most likely a dress. This is most likely a bag. But how sure is it? You would want a network that says this is definitely a dress, like 99% sure that this is a dress. This is 99% it's a bag, instead of I'm fairly sure, maybe like 51% sure this is a dress. And that's kind of what's lost in accuracy. In accuracy, you just know that somehow I got it right. But in loss, now you're actually looking at how sure that your networks got it right. So back to that 80% accuracy example, if you have two networks, they both might have 80% accuracy, but one network might be very sure about every single answer and is 80%. And then for the 20% that I got wrong, it wasn't quite sure. That's a good network. The other network might be for the 80% that I got right, it was like, I'm kind of on the fence, but okay. That's like a low confidence network. That's not a good network. While the other one, it's definitely sure about those 80%. That's a better network. That's a network that you would be more confident. Now let's talk about the different networks that we had here. So we had network A, B, C, and D. These A, B, C, and D networks are different in their own ways. So if we look up here, I have shown these are the different architectures for the networks. So there's different types of networks out there, and there's different architectures for each one of those types. So network A, B, and C are what we call fully connected networks. And what they are is basically, you'll see something called n nodes, and then you'll see a list of numbers. Each list of these numbers tells you how many nodes, and this is actually where the term neural networks comes from, because the nodes are the brain cells of the network. So this is talking about how many brain cells there are per layer. So for example, network A is very, very simple. There's 10 nodes in one layer, and that's it. Network B has 3 layers, 500, 500, and 100 nodes. And then network C is huge. And this just goes to show that your networks don't need to be big. It doesn't need to be a very, very huge network for it to perform well. Because if you look at the accuracies here, let's compare A, B, and C for now. If you look at the accuracy at the very end, network B actually is the one that performs the best. Network A is a tiny bit off. And network C is somewhere in the middle. But let's look at how long it took to train these guys. So over here, if you see the pop-up, I can't move my mouse to highlight it, but if you see the pop-up, you'll see that network B is 73% accurate. Network C is 72. Network A is 71%. But if you look at how long it took to train, network C took 3 minutes and 30 seconds. Well, network A and B only took 2 minutes. So this just goes to show you that with neural networks, it's not always about putting as big of a network, as powerful as you can into it and seeing the result. And this is also kind of the result that you guys are all seeing, that you guys should all be seeing as well. So I have here the leadership board. I also pasted this into the chat if you guys want to check it out as well. Let me zoom in. So some of you hackers have been getting, found out how the code works and hacking the system. But if you look at some of the rankings, there's a lot of networks. Network D transfer actually seems to be the best, and we'll get into what transfer is. But other than that, network D is the best. Beyond that, you can see your C's, your network B's, and all those. And everyone's in the 70-something %. Some are doing a bit better. Congrats on Algis for your custom network. Looks good. But yeah, this just goes to show you that these networks, there's a lot of different types, right? And now let's look at what network D is. Network D, you can see here, it performs a lot better than the other 3 networks. Network D is a different type of network. It's called a CNN, or convolutional neural network. And what that is it's actually a tailor-made type of network for visual data. I won't get too far into it. Again, if you're interested, ask me at the Q&A. I'll be happy to explain it. But it's a network that's designed for pictures. So these are pictures. And as you can expect, it does a lot better, and with a lot fewer nodes too. When you're training, you probably would have seen at the top number of parameters. This is basically talking about how many cells are in your neural network. Network A is 7,000 or 8,000. That's very small, actually. Network B, 700,000. That's all right. Network C is over, what is this? This is 100 million nodes. And that makes sense why it's so slow. There's so many different cells that you need to train, right? And then network D goes back to, it's only 700 again, 700,000. But you're using those brain cells much more efficiently. And that's why it performs better. And then at the very end, we have something called transfer learning. And Jacob will get into the transfer learning a bit later in the slides. But transfer learning, you can see, is the best performing. If we look back on the leaderboard, transfer learning is way up here. Everyone's getting better in transfer learning than any other network, and except for Luke, because he's a hacker. The transfer networks, that's a newer type of machine learning. And what that basically is it's taking a network that is already trained on something similar, and basically using that power to specialize it into this specific task. So it's kind of like a master's program, if you think about it. You're undergraduate, you're generalized, and then you take that generalized knowledge and you specialize it in your master's program or your PhD, something like that. So that's kind of what a transfer network is. Now, at the very bottom, we have a section. This is optional and it's commented out. This is where you can train your custom network. Some of you have already done that. This here, you can play around with a node. So I've talked about what nodes are. I haven't talked about what kernels are. These kernels are for your convolutional neural network. What they are convolutional cells, basically, of your neural network. And now you can try playing around with these numbers. What this does is basically play around with the architecture of the neural network. And you can try different things and see how it works, and try to increase performance. This is a lot of what data scientists and AI researchers do, is play around with these numbers, play around with architectures, to try and find the best network that's specialized for a specific task. So yeah, this notebook is public. So even after this workshop, you can still work on it. But yeah, just go ahead, play around with it. To run these cells, if you want to run them, just get rid of these hashtags, and now you can run them like before. So Yeah, back to you, Jacob.
Awesome. Thanks, Mike. I'll go back to sharing my screen. And I'll be a little bit cognizant on time because I know we only have till 7:30. So what I'll do is I'll focus in on kind of the takeaways we want to get from this lesson, and then I'll just touch on a couple of current applications of artificial intelligence, machine learning, and then we'll open up the floor for any questions people may have. So key takeaways. So the main takeaway we wanted you guys to get from this is that with a lot of these modern frameworks, deep learning actually takes a ton of math and it is a lot of effort, but with modern frameworks, people have abstracted away a lot of that. So it's relatively easy to learn and implement. If you're not familiar with coding, the presence of a lot of code can be intimidating, but I guarantee you, if you spend a little bit of time with it, it is a lot easier to implement than you would think. So one of the things we did in this little session here is we classified these fashion images, and I think the highest scores we got were in the mid 80s, if I have that right, and that's pretty good. To put that into context, the latest research labs, essentially the benchmark of how high anyone has gotten in this data set is 95%. So from this AI 101 session, we got within 10% of the absolute gold standard out there. And I think that's pretty cool. The other thing to realize is when you're making these models and when you're tuning these models, Mike said that that's what a lot of AI researchers end up doing. They work and they tune, and one of the ways they try and figure out what to do with their models is by using context and the domain. So, for example, what we're looking at here is images. So, looking at how other applications of neural networks on images and taking what they've learned and applying it towards your models, or just looking at how even as humans we process images, a lot of that has tried to be reproduced in some of these on some of the leading neural networks today. And then finally, my last major takeaway from this exercise. What they ask you to do?
I don't know, dude. That's why I'm
perfect. And then the last major takeaway from the exercise is that transfer learning is king. So, so Mike mentioned that all those transfer learning algorithms kind of ended at the top. What transfer learning is that it's a network that's all retrained on a different data set. So it's a different data set that's usually quite similar to the one that you're going to be training it on. And through that action of training it on this similar but different data set, a lot of the weight settings that we talked about earlier have already been mostly set. So when the model starts to see your data, it's essentially just fine tuning instead of starting from scratch. So right off the bat, you start to get really high accuracies. If this is something you're interested in and this is something you want to learn more about, I'd highly encourage doing online courses. There's incredible content on online courses. That's 100% of how I learned how to get into this field. And the one that I'd recommend right off the bat is a course called Fast AI. If you just Google it, you can click on the link, and they have machine learning courses and deep learning courses. So maybe what I'll end at is just one of the slides after here. What I wanted to show you guys with this slide is that we looked at images, but there's a whole bunch of other different use cases, as you'd imagine. You can use audio, you can use tabular data. As long as there's a pattern to be found, that's where neural networks really shine. Yeah, and then maybe to bring it more into like a local context, this is an example of some of the work that some of our colleagues have been working on. So there's an ongoing project that they have with Purelator. That's one of our clients. And what they did is they built a chatbot. So the challenge that Purelator had was that there was large call volumes that they got. And typically when they got these large call volumes, what they would do is they would pass that along to their contact center who would try and handle all of these. Now, the challenge is that a lot of these are the same kind of queries that could have been automated away, but there wasn't a system flexible enough to answer people phrasing questions in different ways. So what this team did is they built a chatbot that recognizes text, and even if you hop on the Purelator website today, and you hit the chat function, if you ask them who they are, it'll actually tell you that it was built by IBM's Watson team. With that, I'll skip past the next couple of slides and I'll open up the floor for questions. And I'll end our talking part of the presentation. Thanks everyone for listening to us talk for a long time, and I hope you found the notebooks useful.
So if anyone has questions, they can feel free to just say something in the chat, or you can unmute yourself and start asking your question right now.
Thank you, Jacob and Mike, for coming and accepting to come here, teaching everyone what machine learning really is.
Yeah, no problem.
Yeah, thanks, Kareem.
Thanks, guys, for hosting us.
Hi, I just wanted to ask a question. So you already said, what are kernels again?
So kernels, I can share my screen again. Let me share my screen. So here, you're talking about these N kernels. So kernels are a type of so they're a layer in something called a CNN, convolutional neural network. And what these kernels are they're cells, they're nodes within a neural network, but they don't connect to everything. They are actually only connected to a little area of an image. So if I could use this image as an example, over here, we have 64 kernels, so 64 different patterns that we use to look at this image. So let's say like from like this little bit, this little area. And we have 64 different patterns that we look at that little area, and we scan through the whole image with something that's only that big with that pattern and see if anything matches. And that's very helpful for visual data because in visual data, what we're looking for are little patterns. And so basically we don't need to see the whole image to know that this is a bag. We might, or sorry, this might be a better example as a sneaker. We don't need to see the whole image. We just need to know that it starts off narrow and opens up wide. So that's kind of what a kernel does, is there's a narrow pattern. So 64 talks about the number of patterns. So there's probably one pattern that looks at the tip of a shoe, another pattern that looks at the heel of a shoe, and another pattern that looks at maybe the top part of the shoe. I'm not a shoe expert, so I don't know what that one's called. But those are the patterns or kernels that is used. And that information then goes on into the network, and the network decides what to do with that information and decides that this image basically has those patterns in it, which tells it, okay, that's probably a sneaker.
Mm-hmm. So to increase accuracy, would I have to change in the code like to increase the number of kernels?
So that's not easy for us to say. And I don't think that's easy for anyone to say. Like that's why there's so much research into AI, is because we don't know if we should increase it, decrease it, add more layers, reduce more layers, add fancy new layers, or anything like that. Like with the example of network A, B, and C, adding more doesn't really mean you have better performance. You're actually looking for that sweet spot in the middle. And we don't know where that sweet spot is.
Okay, I see. Okay, thank you. Thank you so much.
No problem.
Could I just ask a follow-up question to that?
Sure.
So you mentioned that we're looking for the sweet spot where the algorithm performs at like the maximum performance while it's still keeping efficient. I was just wondering, since you said that the maximum accuracy that the researchers found with this data set was 95%, I was just wondering how the researchers really sort of experimented with it and managed to find that sweet spot.
So the paper where they got 95%, they're using something a bit different. So they're not actually using the exact same type of networks that we're using. They're not using generic. So like the networks that you've been using are generic, what are called fully connected networks. That's network ABC, or CNNs, convolutional neural networks. That's network D. It's not using those. So they're starting to put more thought into how the network architecture should be. So there's something called like skip layers, there's dropout layers, there's things called transformers. There's a lot of cool, fancy new things that researchers are putting into it. I can't say exactly what it is that the researchers are doing right now. There's so many different types of things. I know one of the latest ones that had really good performance used transformers and attention. And I can do a hand wavy explanation of what that means. But basically, what attention is there's like a network within your neural network that says, okay, only look at, maybe like you see all of these pictures. It doesn't really matter what's on the corners. It kind of only matters like the inner circle. Like if you draw a circle within the box, it only matters what's in that circle. So that's actually what attention means. Attention means, hey, pay more attention to what's in the circle. Don't pay attention to what's in the corner. So that's one of the ways that researchers are using. Another is called transformer, which is instead of just one cell in a network, like a brain cell, a transformer is actually a bundle of cells or a bundle of nodes that does a specific task. But yeah, there's so many different ways like that researchers have been using to like eke out the last little bit of performance out of neural networks, or maybe not last, but like eke out the tiny little bits of like 0.1%, that sort of performance.
I see. Thank you.
I have
problem.
also one more question here. Assuming all of us had the same code, how is there different like percentages? Like how did people get different scores?
Awesome question. That's a very good observation. So what actually happens is neural networks are, I'll talk about the technical first. What actually happened is these neural networks were initialized with random weights, or pseudo-random weights, because computers are never random, it's pseudo-random. So those pseudo-random initializations to your networks cause that difference in performance. So you're gonna end up with just slightly different results. It's kind of like how if you're playing a game, you're not gonna, like if you and your friend both play a game at the same time, you're not gonna be initialized at the exact same place doing the exact same thing. That's kind of the same reason. Now, the more conceptual reason why is neural networks don't do well in deterministic systems. Like Jacob said, it's actually a probabilistic system. So the neural networks don't actually always tell you exactly this is the right answer. It tells you this is probably the right answer. And that's kind of how the whole, like our real world works. Programs, computer programs are not how the real world works. When humans are involved, we're always slightly uncertain about things. Like even when we're sure, we're still slightly uncertain. And that's exactly how neural networks work too. They're 99% certain that this image is a dress, but there's still that 1%. So that's the probabilistic aspect to it. And that causes that uncertainty and that difference in performance.
Thank you.
No problem.
Looks like we have a question or two in the chat as well.
Oh, I see. So we have a question. At the end of the day, what are the optimum numbers for n kernels and n nodes till now? I don't know. I don't know what the optimal is. I can look on the leaderboard, but even the leaderboard, it doesn't tell me. It just tells me that transfer networks have been the best. And Aiden, I think, has, oh, no, never mind. Kareem with Network D has the highest score of 81.3. But we're not sure what the best nodes are. Because like I said, number one, it's probabilistic. So everyone might have slightly different performances. And number two, this isn't a solved problem. There is no solved solution for this is the best network.
So can I ask a question as well?
Sure.
So, well, a couple of questions. You mentioned the transfer networks are probably more optimal, especially specifically to this exercise of finding, let's say, images. But for the way you describe the transfer, the way you described it, it seems that transfer is very specifically designed for a specific task. So would you say that, like in a more generic sense, transfer are a bit less effective on other more generic cases?
Mm-hmm. So actually, that brings up a really interesting topic about generality of AI. And I'll answer your question specifically first, and then I'll broaden it out to the general topic. So your specific question is does it do worse because it's specialized? And normally for neural networks, or even all of machine learning, you're trying to solve a specific task with AI or machine learning. And in that case, it doesn't matter if it does well generally, as long as it does well at a specific data set for the whole data set. And now I need to specify that it's a whole data set. It's the general data set, but it's not all the problems in the world. So for example, our network is trained on those 10 different types of clothing. You throw the 11th one in there. You throw shorts into the mix, and all of your networks will fail. Like it will do very bad on all of them. So you need to specify the problem to exactly what you want and then train it. And it will do very well at exactly the problem that you want it to do well with. Now, in terms of generality, at the rate that we're at right now with machine learning, we're not looking at general, what's called general artificial intelligence. We're looking at specialized artificial intelligence. General artificial intelligence is talking about an artificial intelligence that can do well on everything, have a human-like performance in all tasks or most tasks. And we're not there yet. We are very far from that point. And that point is actually very, very scary, because what if they surpass human performance in all aspects. We don't know what it's doing. It's outthinking us, right? And that's the fear with AI of a lot of people, that it's going to take over the world, Skynet style. And we're not there because we're not at generalized AI. We're at specialized AI. And so all of the problems that we have right now are specialized for AI. For example, the example of IBM's Deep Blue with chess, you ask it to sort clothes, it will not do it well. You ask it to play chess, it will beat the grandmaster, right? And that's where we're at. We can, other AIs out there, like Netflix has really good AI in suggesting movies. You tell it to suggest songs, it can't do that. It's just not what it's able to do. So I hope that explains
Thank
it
you.
a little bit.
Yeah, and I had just a quick another follow-up on everybody's asking about the kernels and nodes. So let's say there is an optimal, or at least an optimal number of nodes which would get you to a 95%, like the gold standard. Could you not build another network on top of your network and put those as inputs and you know what I mean? I mean, I know it'll take a lot of more computational power, but it ultimately theoretically could work, right?
Mm-hmm. You see both Jacob and I smiling. Yeah, that's another field or subfield of AI called meta learning. And that's exactly what it does. A lot of networks nowadays take advantage of that. Like I was saying about attention. Attention is basically training a sub network within your network to tell your network what to look at. So, and then there's other networks out there that say, okay, to tie in what you were talking about before with the generalized problems, there are networks now that look at a problem and tell you what type of networks would work well for this problem. So it's like a network controlling other networks to solve your problem. So now instead of just sorting closed, you can have a network that looks at the problem and says, is it movie recommendation? Is it music recommendation? Is it clothes sorting? Is it playing chess? And after looking at that, it says, okay, if it's movies, go to the Netflix network. If it's music, go to Spotify. If it's clothes, go to what we built. If it's chess, go to IBM Deep Blue. So that's some of what we're doing, is building that meta learning as well. And so that's a very, very smart idea, and that's a lot of what researchers are doing. So good question.
Thank you. Thank you.
Just a small question. Yeah. So you were telling about like how to get the best score from looking at the graphs. I was just thinking like for the sweet spot, right? So from the graphs on the TensorBoard, I was thinking, do you usually find the best point with like a program, or do you just find like the derivative of the curves to see which one is the highest, or is it more of like what's the method to find out when you have like a lot of curves?
Right. Okay. So let me share my screen again, and I can explain the curves a little bit because we never got a chance to go into this. Neural networks can be a whole course. So we didn't dive into this, but let me explain what the curves are first, and then that might answer your question. So the curves here are actually talking about how we're not looking at a single point in the curve. We're looking at the actual result. So for example, if we're looking at all of these networks, we would choose the transfer network because on the x-axis, this is talking about epochs, number of times it's gone through the examples or the data, the training data. So by the 10th time, it is 80% accurate, at least for me. So you would choose that one. And you would assume that by 11, it's going to get even better or about the same, right? But you can see that it learns very quickly at the very beginning because it doesn't take much for it to get to 50%, right? And then it's a little bit harder. It's a little bit harder. And I know all of you in school know. Getting that last like 5% is much harder than just barely scraping by. The first 50% is much easier than getting from 95 to 100%, right? So that's basically what this network is also, these curves are also showing you. So you're not actually looking for the best point in the curves. So I hope that answers the question.
Yeah. Thank you.
No. Yeah, no problem. And but you also mentioned a good point about searching for those numbers, like the number of kernels, the number of nodes, and that's actually called something called a hyperparameter optimization. So parameters are what we call those nodes and those weights that Jacob was talking about, and hyperparameters are what we call the numbers that dictate the architecture of the neural network. And what a hyperparameter search is looking for the best number of best numbers for hyperparameters. So that's typically nowadays in the industry how we work. We don't actually try these by hand, these networks by hand. We write a program that goes through and tries all of these numbers, and we have a general sense about like, okay, the number should be between like 25 and 200 nodes for this layer, and it should be between 3 and 5 layers, something like that. And then the program will just take all night, maybe take a week, going through all of the networks, going through all of the data, trying every single combination of the numbers of different architectures, and then spit out, okay, this is the best, and it's probably going to be like somewhere around 90%. That's my guess about what's the best that we can get with a simple network like what we have. I see that we have another question from the chat. Hi, notice that with every epoch, the accuracy of the model increases. So I just had two quick questions. Could you briefly explain what an epoch is, and does this mean that each epoch/training cycle mean the model should be more accurate? Yes, okay, good question. I never explained what an epoch was. An epoch is a cycle, a training cycle. It's a cycle through all of the data. So epoch 1 means you went through the data once. Epoch 2 means you went through it twice, or the second time that you went through. So yeah, every time you go through, you would expect the network to get better and better and better and better. But you hit a point of diminishing returns. It approaches an asymptote, which is the theoretical maximum that this network can ever get, right? And you see that with the curves. It flattens out. So that's why, like, typically with these networks, it's better to look at how to build the networks than to just wait till it trains to epoch 10,000, because by the time you get to epoch 15 maybe, or like 20, you get a sense of where the asymptote is.
Hi, I have a couple quick questions.
Mm-hmm.
Is transfer learning just better because it sees more unique data, or what makes it better other than it just seeing more data that is unique, I guess?
Mm-hmm. That is a good point. Transfer learning does see more unique data. And back to, I think, Andre's question about generality, it becomes more general because of the data that it's seen. That is part of it, but the main part of it is actually, it just trains much faster. It learns so much faster because it already kind of has a foundation of knowledge built into the network already, pre-trained into the network. A good example of that is nowadays with image recognition. There's something called ImageNet that is years old now, but it's like, it's the standard for image recognition. And the use nowadays, like what you would typically do for image recognition is you just take a network that was pre-trained on ImageNet, and you train it to your own images, because most of the training that goes into the network is just how to recognize things in images. And ImageNet does that already. It just doesn't train it specifically to the exact things that you're looking for. So maybe you're looking to train a network to classify between cats and dogs. A lot of the training goes into classifying what a hair is, what an ear is, what an eye is. But you don't really need to train that if you have ImageNet, because it's already pre-trained into the network. So it just becomes so much faster. All you need to know is dogs and cats look slightly differently. So that's the information that you need to train into the network, instead of starting from square one and training what is an eye, what is an ear, what is a nose, that kind of thing.
I see, that makes a lot more sense. Could I actually get you to go into what unsupervised learning is about as well?
Yeah. We can briefly go into it. It's a huge field.
Actually, Mike,
even
before
if
you
I'm
go
talking,
into that, I actually need to hop off the call. So thanks everyone. I'll let you handle the rest of the questions.
Thank you so much, Jacob.
Okay.
Appreciate it.
Thanks everybody.
Thanks, Jacob.
Thank you, Jacob.
Thank you very much.
So let's talk about unsupervised learning. It's a very, very interesting field. And even if I talk all night, we're not going to get like anywhere close to all of it. But the main intrigue of unsupervised learning is how does it categorize, right? Like that must be what you're thinking of as well. And the way that it categorizes is with clustering algorithms. So there's different types of clustering, but most of them start with something called a distance function or a loss function or something like that, which is to say, what is the distance between two data points? And this distance is kind of a measure of how similar they are. If they're very similar, then their distance is very small. If they're very, very far apart, that means that they're not similar at all, right? So even more of an example, let's talk about colors. If you just have a data set of just colors, and you want to cluster it into red colors and blue colors, right? So then you would probably just, I don't want to get into hashing, but let's just talk about the RGB values for the colors. If that's something that you guys are familiar with, you can just look at the RGB values. If the R values are very close, like you just do a absolute subtraction of the R's plus absolute distance or subtraction of the blues and the greens. Like L1, L2, it doesn't really matter what you use there, but that can be your distance function. And then your clustering algorithm can just go through and basically look at the distance between all these different points and create a cloud map of two different clusters. Like one cluster can be like mostly blue colors and the other can be mostly red colors. And that's how it clusters. And that's unsupervised learning. So then it can come back and say, I found these two different clusters. And you can say, oh yeah, that makes sense. These look all red, these look all blue, right? So that's kind of what it does. And that's the use of it in industry as well. It's the first step to clustering everything together, and then you look at the clusters and you make sense of what the clusters mean.
I see. Thank you.
Can I ask a real quick question?
Mm-hmm.
So I just want to, like, before you mentioned for our example, like for one of the learning example, there was like 100 million parameters, right?
Mm-hmm.
So like, how do we actually go about deciding like how many parameters or like what parameters we choose? Like I can't imagine more than maybe like only the pixel values for the example we have for as address. Like what other parameters would we typically feed in?
Okay. So I think I need to clear up a misconception first, and then I'll dive a little bit deeper into it. So when we're talking about parameters, we're talking about the number of nodes. So a parameter specifically in neural networks is the weight and the bias. So each node has a weight, that's one number, and a bias, that's another number. So we're not actually talking about the inputs of data. I know like in computer science and programming, that's also what we call parameters, like a parameter is in a function, which is the input. We're not actually talking about that in terms of the neural network. What we're calling parameters is more of, you can think of it like the constant variables, right? So sometimes we need way more than the number of pixels, because think about, I'm not sure if you guys know about kernel functions, but you can take a small amount of data and you can expand that out into a lot more. So for example, our images, right? Like with our images, there are 28 by 28 pixels. Within each of them, there is 256 different light levels. So if you think about that, that's 28 by 28 to the power of 256. If you type that into Google to try and calculate it, it will tell you infinity. That's the number of different combinations that the input could be. So your parameters isn't just looking at the pixels, it's looking at every single possible value of every single one of the pixels. The inputs are looking at every single possible value. So that's why the number of parameters can get that big. Does that answer the question?
Yep, awesome. Thank you. I was actually thinking wrong about the parameters. Now it's more clear.
Okay, awesome. Yeah, I figured that's probably where the misconception came from.
Hi there.
Hi.
I just have a question about classifier and regressor models using neural networks. Could you just describe the differences between the two and like kind of how neural networks tie into these models?
Sure. Simply, classifier classifies into different. Sorry, using class too many times. Classifiers classify into different classes. Classifier basically tells you what something should be. Like for example, our clothing, Fashion MNIST. It tells you, okay, it should be either a shoe, it should be a dress, it should be a t-shirt. That's a class. A regressor model actually tells you a number value. It's a continuous spectrum value. So instead of that type of problem, which is like just putting things into classes, you're talking about something like let me give an example. If I am got it. The example that Jacob was talking about with the house, given the square footage, given the number of washrooms, how much would it cost? So there's no classes that you need to put it into. You know it's a house, right? But you're talking about a continuous spectrum of possible values. It could be 300,000, it could be 500,000, it could be anywhere in between, right? So that's a difference in types of problems there. Basically, if there's only a handful, or you can count the number of possible answers that the problem can come up with, that's a classification problem. If you can't, if it could be anywhere within a spectrum, that's a regression problem. Does that help?
Yeah, it does. Thank you.
Awesome. No problem. So any other questions?
Hello, sir. Hello.
Hi. Hi.
Are you hearing me, sir?
Yep.
Okay. Please, can you still explain to me hyperparameters and difference between parameters and hyperparameters in relation
Sure.
to SVM?
In relation to SVMs, okay. So SVMs are a bit different. What we were talking about here is the hyperparameters in a neural network. I'll have to go back and check my notes for SVMs. But vector machines, I'm not sure if they have hyperparameters. I guess the hyperparameters would be the size of your model. So the size of your model would be the hyperparameters in the case of SVMs. But yeah, can you vary? Yeah, I'll have to check my notes on that. Yeah.
Okay.
So are there any other questions?
Quick question. So I did a bit of machine learning, and I use the sklearn library, and there's this function called grid search parameters of the model, and by providing like a list of values for each hyperparameter. And I was wondering if there was something similar when dealing with the torch library for networks.
Sorry, you're cutting in and out a little bit, but I think I got the gist of what you're asking, which is hyperparameter search for PyTorch. Is that correct?
Yeah, that's my question.
Okay. Yeah, so hyperparameter search in PyTorch. Actually, you can use both. You can use hyperparameter search from sklearn for PyTorch. The libraries aren't mutually exclusive. PyTorch, I believe there's something in there for it, but I believe the sklearn one is more mature for grid search at least.
Okay, thank you.
Thanks for that in the chat, Jiagu. The C and the gamma in SVMs. Yeah, so those I think you might be right in that they are parameters. Hyperparameters only matter when it's talking about the construction or the architecture of your model. So it's not the parameters itself. So I think you got it right there. In that the C and the gamma are solved for the model itself. So they would be parameters, while hyperparameters would talk about something more on the lines of, I don't know, for SVMs, I guess maybe like number of kernel functions. You would kind of define the kernel functions. They would be more hyperparameter-esque, but that wouldn't be a specific parameter. That'd be a class of kernel functions. So any other questions?
Yeah, I guess I have just one last question. Just to break it off from all the machine learning and AI explaining, this is like a question relating to your work, basically. So like obviously like with machine learning, there's like the application aspect and there's the behind the scenes math kind of thing. So like in your works, do you find that you're dealing with more of the mathematics behind it and analyzing which models and which, I guess, mathematics tools that you should use? Or do you find that you're dealing with more of the front end things of dealing with clients and providing them with the best potential prototype, I guess?
Yeah, thanks for that question. I feel like I was probably helping a few of you out with homework assignments, or at least exams. So yeah, that's a great question about in real work. So I have to first state that both Jacob and I, we are consultants. So a big part of our jobs in itself, like consultancy, a lot of it is presentation and meeting with clients and talking about it. So that's big part of our jobs in itself. But then in the industry, for data science, for machine learning engineers. So my job as a machine learning engineer isn't actually to build these models. It's to be familiar with these models, but build the systems that facilitate these models. So sometimes I'm building systems that can automatically train these models. Sometimes I'm building systems that can that work efficiently for specific models that data scientists like Jacob would hand me. And now for Jacob, a lot of his job is looking at the data and doing statistical analysis on the data. So he might be looking at the data and say, okay, this type of data, you don't need a neural network. It's better to use random forest. Or this type of data, it's really good to use, maybe it's recurrent, so LSTMs or something like that. So his job is more looking into the data, but I wouldn't say either of us are implementing backprop on our own. Like where our jobs are to be, like our skill set requires us to be familiar with these libraries. So PyTorch, TensorFlow, sklearn, we're familiar with these libraries. Of course, we're still learning because they keep on updating them, but like we're familiar with these libraries because they provide us with these tools that we don't need to do like differential equations on a day-to-day basis, basically. I don't think I've ever done differential equations since graduation. So that I hope that kind of answers your question a bit. It's more to like just know and understand what the benefits of different models are, what the benefits of different libraries are, and different packages to help you, basically the tools.
Yeah, thanks for answering. That definitely helps. I'm a little bit more familiar on the consulting side and I have some AI experience myself. So that's a really good answer. I do have some other questions, but I guess I can connect on LinkedIn if you don't mind to ask those, because I've been talking for 2 hours and I don't want to take you too much of tonight's time.
Yeah, no problem. Yeah, if, all of you guys feel free to reach out to either Jacob or myself on LinkedIn. We'd be happy to tell you guys more about the industry.
Yeah, definitely. It's been it's been a good 2 hours now, over 2 hours actually. So I'd like to just thank everyone for attending today, and I'd like to thank you, Mike, so much for taking out the time to speak with us today. I think you really did educate a lot of people today and inspired a lot of students as well, which is really awesome. So if it's okay, we will end the session here today. But again, like Mike mentioned, please feel free to reach out to him on, if it's okay with him, to reach out on LinkedIn. Maybe he can ask a few questions.
Thank you very much.
Awesome. Thanks guys for attending. Yeah, awesome questions.
Yeah, and thank you, Hani, for moderating.
Yeah, no worries. No worries.
Okay. Thanks, everyone. Have a good night.
Thank you. Bye-bye.
You too.
Bye.